Hey guys, welcome to All Electronics. I'm Gregory and today we are going to take a look at how an analog frequency divider works. Let's go! So guys, we have here the setup on the bench, we have the circuit working here. In a moment I will explain the block diagram and the circuit diagram. We are generating a 1.6 GHz signal at a level of 0 dBm and the output of the board is going to the spectrum analyzer here at the top. We need two power supplies to make it work, as I will explain later. We have the biasing supply of the amplifier and the biasing supply of the mixer. This connector is the input of the circuit where the 1.6 GHz signal arrives. The signal is divided by 2 in this circuit. And here at the output we have an 800 MHz signal. This topology is an analog frequency divider or regenerative frequency divider. And we will understand this microstrip construction later. Here with the spectrum analyzer we can see the output of the circuit. We need to ignore these two tones here around the output tone because they are generated by my wireless microphone. So if I turn off my microphone, these two sidebands here, sidebands will disappear, so they don't make part of the circuit. You can see that we have a small leakage of the input 1.6 GHz signal, but the main tone here is the output at exactly 800 MHz, that is half the input frequency. The output power is negative 15 dBm and this third tone here is the third harmonic of the output. So we have 800 meg, 1.6 gig and 2.4 gig here. It is interesting that the second harmonic is overlapped here with the input signal and they are lower because I have a trap at 1.6 gig in the circuit. This topology is called a regenerative frequency divider because it uses positive feedback to generate an output tone of half the input frequency. The input 1.6 GHz in this example is applied to the input of a frequency mixer. The mixer has conversion loss, so the signal here at the output is weaker than the input signal. So we use an amplifier at the output of the mixer to increase the signal level and we feedback the signal to the other input of the mixer. This topology is quite interesting because the only frequency where positive feedback can happen here in this closed loop is at half the input frequency. So if we imagine that we have F here as the input frequency, F over 2 here, the signal is amplified and here we have also F over 2. This is a possible condition for the mixer because we are mixing F with F over 2 and one of the conversion terms will be at F over 2, okay? And this condition also have the property of phase conjugation. So the phase of the output signal is switched in a way that positive feedback happens around this amplifier here. As the amplifier has gain, we can sustain oscillation. The oscillation will be at F over 2. So we can divide the signal. If the input is 1.6 GHz, this feedback will happen at 800 MHz. We need to maintain proper levels at the input of the mixer and we need to take care of the compression of the amplifier. If I try to increase the signal level, we start to get spurious oscillation at other frequencies because now we have third order modulation in the mixer and the harmonics of the amplifier caused by compression start to be intermodulated and generate other paths where the positive feedback can happen. So we need to have proper level at the input and proper biasing of the circuit. The signal arrives at this input connector and we have a trap for the output frequency here to prevent the output frequency to go backwards here in the input ports. So this trap here made by this transmission line and this transmission line is a trap at 800 MHz. This node is the output of the mixer and here we have the amplifier. We need to amplify only the output frequency 800 MHz. So we need to prevent the 1.6 GHz input signal to go to the amplifier. So we have this trap here that works at 1.6 GHz. The two networks are composing a duplexer where you have frequency multiplexing. So here at the output node of the mixer, the 800 MHz signal can go to that direction and can't leave by the input port. And the 1.6 GHz signal can arrive at the mixer and can't go to the amplifier. The output of the amplifier here is feedbacked to the mixer here, so with this transmission line here. So this is the closed loop we saw on the block diagram. Only a small fraction of the amplifier power is coupled to the output with this directional coupler. So power traveling from the amplifier to the mixer, part of the power is coupled with this coupler and goes to the output connector. I placed also here at the output a trap at the input frequency to prevent any leakage of the input frequency 1.6 GHz to go to the output. This is why the output is so clean, guys, because we have the input duplexer and we also have this output notch filter at the input frequency. This topology was used a lot in old vacuum tube circuits. This was the way to frequency divide a signal. Today, almost all the applications of frequency dividing is made using static logic circuits, flip-flops and counters. But this technique can still be useful for very high frequencies, microwave bands and millimeter wave bands. In these high bands, static dividers consumes a lot of power and generates a lot of noise, and this technique can be useful in this situation. The input signal leakage is almost 50 dB below the output, so very nice isolation of the input to the output. And you can see that harmonic distortion of the output is also very low. The third harmonic here of the output is at negative 40 dB in comparison to the power of the input. The low distortion happens because the amplifier I used is tuned to the output frequency, as we're gonna see now in the circuit. Prepare your coffee because now we're gonna take a look at the circuit diagram. If you are liking the video, please subscribe to the channel and give a thumbs up to help me grow the channel. Let's go! So guys, the input network is the duplexer made by the A network and the B network. So we have here at the input two quarter wave transmission lines that isolate the input from the mixer at 800 MHz. We can understand this because this transmission line will generate a short circuit here at 800 MHz, and this transmission line will transform the 800 MHz short here in an open circuit here. So for the mixer, the 800 MHz path from the mixer to the input is an open circuit here. This transistor is a pseudomorphic high electronic mobility transistor, and it is running in the circuit as a passive mixer, and you're gonna understand it later. The B network is made by two copies of this network here, but now the quarter wave is half because this network needs to work at 1.6 GHz to prevent that the 1.6 GHz that arrives here in the node of the mixer goes to the amplifier. So here we have the 800 MHz because the 800 MHz can pass through the network and the signal is amplified by this common emitter amplifier here. The common emitter is biased by the same network here, the C network that we saw here at the input. This network is used to bias the transistor and to maximize the gain of the amplifier right at 800 MHz. So this transistor is operating as a class A tuned amplifier. The peak gain at the right frequency is given by the biasing network here, also made by transmission line transformer. We can see that output of the mixer is amplified and we have the feedback action by this transmission line to the input of the mixer. The D network is the output coupler that couples part of the signal that flows from the amplifier to the mixer to the output. And here at the output we have a trap at 1.6 GHz to isolate the input signal from the output of the circuit. This coupler is very important because any mismatch at the output here and any mismatch generated by this network will generate reflection, and the reflection will be absorbed by this resistor here because the reflected power is flowing in the backward direction and is coupled to the resistor here. And this is how the circuit works. It's very important to have a balanced mixer here, because if the high power of the input leaks to the output of the mixer, the amplifier will amplify the wrong frequency component and we will not have the frequency division we want. So the balance operation is done by this transistor acting as a passive mixer. This transistor is not acting in the active region. We have here only channel modulation. So we can see that we don't have bias on the drain of the transistor. So we don't have DC current going in the drain of the transistor. So we are not in the active region. The power that arrives here at the gate of the transistor will modulate the channel conductance. So we don't have any amplification. This is important. We don't have amplification of the input signal to the drain as if it was an amplifier. We only are using the gate to modulate the conductance of the drain. So we can think as the transistor as a variable resistance here, shunting the power of this node. If this resistance is changing by the input signal here, we are going to modulate the power here because we are modulating the reflection coefficient of this node. So as the power here is modulated by the input signal, we have the frequency mixing effect needed to generate the down conversion component. What is the down conversion component, guys? Is the F over 2, because we are mixing F with F over 2, and the down conversion component of the mixer is F over 2. So guys, I hope you enjoyed this video. If so, please subscribe to the channel, give a thumbs up, and I see you in the next video.